Thank you for introducing me. My name is Ki-Wan. I'm a PhD student under Professor Yun-Jae Kim in Korea University. My presentation topic is simulation of combined ductile brittle fracture for API X80 under impact loading. This work is collaborated with POSCO in Korea. Impact loading under high strain rate is one of the severe conditions leading to fracture. Large or full-scale impact tests, such as DWTT or impact tests, can provide valuable information. However, their execution is limited due to the cost and safety concerns. So we want to analyze the behavior under impact loading using numerical approaches. When the temperature is lower than specific temperature, the combined ductile brittle fracture can be occurred, and the temperature is called as DBTT. The DBTT depends on the shape and the dimension of the specimen. So to analyze the combined fracture in structures, a systematic procedure quantifying ductile and brittle fracture should be required. Under impact loading, material hardens due to strain rate hardening and softens due to thermal softening. Fracture strain and the ductility decrease and the strength increase due to strain rate hardening. And the temperature under impact loading increases due to the adiabatic heating, and the increased heat softens the material. It is called thermal softening. So this is how to consider both strain rate effect and adiabatic heating effect in our study. We use Jones-Cook deformation and fracture model for ductile fracture simulation under impact loading, and we use critical stress-based fracture model for brittle fracture simulation. So finally, these parameters should be determined to simulate the combined fracture under impact loading. The red-colored experiments were used for model determination. Smooth round bar tested various temperature, SCNT and CVN tests at room temperature. And the blue-colored tests, CVN tests at various temperature and DWTT at various temperatures were used for model validation. This is the model determination procedure. Firstly, the Jones-Cook deformation and fracture model were determined. The model under quasi-static states at room temperature were determined using smooth round bar test and SCMT test at room temperature. The temperature-dependent parameters K and D5 were determined using smooth round bar test at various temperatures. The strain rate dependent parameters C and D4 were determined using instrumented CVN test conducted at room temperature. The critical stress-based fracture model for brittle fracture simulation were determined using CVN simulation using the determined Jones-Cook models at -60°C. So determined models are validated by simulating DWTT at other temperatures. The experimental for model determinations are shown here. The smooth round bar test at various temperature and SNT CVN test at room temperature. Firstly, the true stress strain curve at room temperature was determined by simulating experimental engineering stress strain curve. Total 3 sizes of elements were used for simulation, from 0 to 1 to 0.3 millimeter. The temperature-dependent parameters of Jones-Cook deformation model K were determined by fitting the variation of yield strength with temperature. So the final value of 0.7 was determined. Using the determined model, the experimental engineering stress strain curve at -100°C and 60°C were well simulated, and the parameter K was independent with element size. And next, the strain rate dependent parameter C was determined using CVN tests conducted at room temperature. Left figure shows the variation of load displacement curve with increasing value of C. With increasing value of C, the load displacement curve increased, and the final value of C, 0.18, was determined by predicting the experimental maximum load. And the parameter C is also independent with the element size. The Jones-Cook fracture model on the quasi-static state at room temperature was determined using SENT tests conducted at room temperature. Firstly, the critical damage value DC was determined by simulating experimental crack initiation, and it is determined as 1. And secondly, the value of D2 was determined by simulating crack initiation, and this is the final multi-texture fracture strain. And the parameter D2 is independent with element size, and the critical damage value DC was dependent on the element size. The temperature-dependent parameter of Jones-Cook fracture model D5 was determined using the fracture strain with temperature. And for API X80, the fracture strain is independent with temperature, so this term is neglected in this study. The strain rate dependent parameter D4 in Jones-Cook fracture model was determined using CVN tests at room temperature. The crack growth accelerated with decreasing value of D4, and the final value of D4 was determined as minus 0.28 by simulating the experimental CVN energy, and the value of D4 is independent to element size. And the critical stress-based fracture model for brittle fracture simulation was determined using CVN simulation with determined Jones-Cook models. So with increasing the value of critical stress, the significant load drop deaccelerating, and the relationship between critical stress with simulated CVN energy shows a linear relationship as follows. The determined model was validated by simulating the tests conducted at other temperatures. When the temperature is lower than minus 60 degrees Celsius, the load significantly decreases, and it is because the brittle fracture. And for DWTT, the significant load drop can be shown even at 0 degrees Celsius. Firstly, the Jones-Cook deformation and fracture strain-based model for ductile fracture simulation was validated by simulating ductile fracture impact tests. The CVN test at minus 30 degrees Celsius and DWTT at 0 degrees Celsius were well simulated with determined Jones-Cook model. And next, the combined fracture model was validated by simulating combined fractured DWTT. The critical stress value was calculated based on the relationship determined by CVN simulation, and the experimental load displacement curve and the fractured surface were well simulated. So using the determined and validated model, the effect of strain rate and adiabatic heating was analyzed. The 3 cases were assumed. The first case is considering both strain rate and adiabatic heating effects, and second case is neglecting the adiabatic heating effect, and the third case neglecting both effects. The solid lines are the result for case 1, and dashed and dotted line represent the case 2 and 3. So by neglecting the adiabatic heating effects from case 1 to 2, the load increased due to, and by neglecting both strain rate and adiabatic heating effect, the load decreased in ductile fracture simulation. And the same 3 cases were assumed for analyzes the effect of strain rate and adiabatic heating on combined ductile brittle fracture simulation. And that figure shows the simulation for CBN test. And by neglecting the adiabatic heating effect, the maximum load increased, and by neglecting the strain rate effect, the maximum load decreased. However, by neglecting the adiabatic heating effect, the initiation of brittle fracture accelerated. However, in combined ductile brittle fractured DWTT, the very similar result with that for ductile fracture DWTT can be shown. So the effect of adiabatic heating is much significant in the small size of specimen. This is the calculated temperature rise in CBN and DWTT simulations at the maximum load point and twice of the displacement at maximum load. So the temperature increase in CBN simulation is represented as solid line, and therefore DWTT simulation is represented as dashed line. So the higher temperature are calculated in CBN simulation due to the small size of specimen. Let's summary and conclusion my presentation. We proposed a systematic procedure for FE simulation under impact loading. So the proposed procedure was validated using by simulating the tests at other temperatures, and the effect of adiabatic heating and strain rate are analyzed in this study. And the adiabatic heating effect can be significant in small size such as CBN test. And thank you for your attention.